Okay guys, welcome back. Today we're going to look at geometric series. This is Math Notes 10.3.1. We basically have talked about geometric series back in Integrated 1. We talked about geometric sequences. So now we're going to apply the same things we learned about the difference between a sequence and a series with arithmetic to geometric concepts now. So if you remember, a geometric sequence is based on an exponential equation. So our exponential equation is y equals ab to the x. In this case, we're going to rewrite that as t of n equals a times r to the n minus 1, where a is our first term, r is the common multiplier, the ratio, which is what we had for b when we were doing exponential equations. So let's take a look at it. Geometric series is the sum of the terms for a geometric sequence, so t of 1 plus t of 2 plus t of 3 all the way out to t of k, which would be our last term. The total for the sum of a finite geometric series, a series that ends. If you don't know this word, infinite means it goes on forever, or infinite means it goes on forever. Finite means that it stops, it doesn't go on forever. So for a finite geometric series is s of k equals r times t of k minus t of 1 over r minus 1. I'm going to zoom in a little on this because it's probably hard to see on your screen. Over r minus 1. That is equivalent to saying a times 1 minus r to the n over 1 minus r. So let's break these terms down real fast. So t of k is the last term. T of 1 is the first term. R is your multiplier. So we have the multiplier times the last term minus the first term over the multiplier minus 1. That's also equivalent to another way to say the first term is a times 1 minus the multiplier raised to the last position over 1 minus r. Be careful with these. Notice that in this one it's r minus 1 and here it's 1 minus r. Just make sure you write those down properly. For example, either formula can be used to calculate the sum of the series. Here we have 1,000 plus 600 plus 360 plus 216, which has an a of 1,000. So this is your a. Could also be written as your t of 1. And if we wanted to sum the first 5 terms here, 1, 2, 3, 4, 5, the sum up to the 5th term would be your multiplier, which is 0.6, times your first term, which is 1,000. Let's start over on this one. So sum of the first 5 terms, this is your multiplier, 0.6. This whole thing is your last term in the series, your t of k, which is going to be 129.6. But instead of writing 129.6, what they've done is they've gone and plugged in an n of 5 to this equation up here. So 1,000 times 0.6 raised to 5 minus 1, which is 4. So this parentheses is going to equal 129.6. Then we subtract 1,000, and then we have 0.6 minus 1, which gives us 2305.6. If we use the second equation here, then we have 1,000 times 1 minus 0.6 to the 5th over 1 minus 0.6, and we get the same answer. For an infinite series, with an initial value of a and a multiplier or common ratio of r, we can use this equation. Now it's worth noting here that to use this infinite series, this r has to be, the absolute value of that r has to be between 0 and 1. Or if it's not an absolute value, it has to be between -1 and +1, and it can't equal 0. So be careful with that. If we've got a multiplier over 1, we can't use this equation. This equation just says that we take the first value over 1 minus the rate. So in this last example, our initial value was 1,000 over 1 minus 0.6. So the sum of that infinite series is 2,500. Remember what we're actually finding. We find the sum. We're finding the area underneath. Having trouble drawing that straight line there. The area underneath the curve. So we have an exponential decay equation. We're saying that the area under here that starts at 1,000 is going to be 2,500. Let's look at another example I have on the next slide. I've started us off with this geometric series, 100, 50, 25. So we should be able to see pretty quickly that the common multiple here is 1/2 or 0.5. So we're multiplying by 1/2 to get to the next step. Our first term, t of 1, is 100. To write the equation for t of n, we're going to use a times r to the n minus 1. So we're going to say 100 times 0.5, which is the same thing as 1/2, to the n minus 1. And there we go. If we wanted to sum, say, the first 5 terms, we would go ahead and first thing we'd have to do is find t of 5, because we're going to need that t of n. So this would be equal to, our rate is 0.5 times t of 5 minus t of 1 over 0.5 minus 1. So let's go ahead and solve this out. So we need to find t of 5. So t of 5 equals 100 times 0.5 raised to the 5 minus 1, or 100 times 0.5 to the 4th power, which gives us 6.25. So 0.5 times 6.25 times, or sorry, minus 100 over negative 0.5. So on the top we have negative 96.875 over negative 0.5, which would give us positive 193.75. So the sum of the first 5 terms is 193.75. We can check that real fast, but since this is this is just the 5th term. We know that our 4th term here would be 12.5 and 6.25. So if we just add this up ourselves the long way, we say 100 plus 100 plus 50 plus 25 plus 12.5 plus 6.25 Sure enough, we get 193.75, which is what we had right here. If we wanted to find the infinite sum, the sum to infinity, we take our a value, which is it's not 0.5, our a value is our first term, is 100, over 1 minus 0.5, so we have 100 over 0.5, which is 200. All right, guys, I'll see you next time.